Welcome, and thank you for your interest. Over the next 20 minutes, we will provide an overview of standard industrial and next-generation aeration controls. This information will help you understand the importance of aeration controls at your plant and how the performance of these systems can impact plant performance. To better understand the role of aeration controls, let's first review what we're trying to control. Leading up to today, the regulatory focus of the industry has been on oxygen depletion and toxicity issues. To meet these requirements, plants needed to deliver percent BOD reduction and nominal 30/30 effluent limits. The plants that we designed featured a series of physical and biochemical, mostly aerobic, processes. Today, the focus has expanded to include nutrients, and treatment performance is now equal to Six Sigma quality with effluent concentrations in the low single-digit parts per million range. In terms of biological treatment, we now rely on sophisticated processes that require confident control of the dissolved oxygen for various operating conditions. When we think about controls, our focus should be on the operational requirements for the plant. This slide highlights the processes commonly used today and the design and operating requirements for these processes. We have moved past aerated lagoons, conventional activated sludge, and extended aeration. Today, plants provide BNR and ENR performance and use processes with anaerobic, anoxic, and oxic operating conditions. Our design philosophy has shifted as well. While we continue to focus on plant capacity, operational flexibility is much more important. So we often see plants with multiple process trains and a large number of operating zones. Because the biological process has become much more specific, there are critical biomass, aeration, and chemical balances to maintain for process performance. For the operator, optimized process performance is almost intangible. Consider the limitations associated with traditional operating practices. Grab sampling no longer provides the data nor the timeliness to dial in the process. SRT control requires regular monitoring and adjustment. Aeration, which used to be aeration to excess, is no longer acceptable, and stringent average effluent limits leave little room for operational error. From our vantage point, controls are being integrated into plants to reduce the operational requirements on staff. However, there needs to be a larger discussion about the performance of these automation systems. Let's step back and consider what we are asking our operators to execute day in and day out. First, we know that everything is interrelated. For example, aeration is required because it supplies oxygen. However, internal recycle loops also represent an oxygen source. So, what level of aeration control is required? Let's first assume that the aeration system is operated at a constant rate and look at the impact of load variation. For the oxic zones, a 20% increase in oxygen demand will reduce the residual dissolved oxygen from 2 mg per liter to 0.5 mg per liter. If the process objective is nitrification, this will essentially stop the nitrification process. For anoxic zones, a 10% decrease in oxygen demand will raise the residual dissolved oxygen from 0.5 mg per liter to 1.5 mg per liter. This will essentially stop the denitrification process. This raises the question as to whether the loading to the wastewater treatment plant varies by more than 10 to 20%. Because most plants are built for some future or peak capacity, we know that there will be an increase in load over time that is well in excess of these values. It's not uncommon to see 30% load at startup. For municipal applications, diurnal flow variations occur every day, and these variations are well in excess of 10 to 20%. Based on this figure, we are looking at a 4-to-1 variation in applied load. As online instrumentation becomes more common, variations as shown are the norm. Here we're looking at influent ammonia, and variations approaching 5-to-1 are present on a daily basis. Now let's look at this from an aeration control perspective where the loading is constant. For the oxic reactors with a target residual DO of 2 mg per liter, a 5% variation in aeration will vary the operating DO from 1.6 to 2.3 mg per liter. For most plants, This is an acceptable level of variation. However, a variation greater than this could start to impact process performance. For the anoxic reactors with a target DO of 0.5 milligrams per liter, the same 5% variation in airflow will vary the residual DO from 0.1 to 1 milligrams per liter. Now we're starting to impact process performance. The discussion up to this point reinforces the challenges that the operator faces in running a modern plant. Let's move on and review the control systems that we use for aeration. Many plants today have a SCADA system to collect information with PLC and PID controllers to operate selected functions such as aeration. In terms of the control system, there are two main parts: the physical equipment, which includes the instruments, valves, actuators, and blowers, and the controller, which converts input data into output commands. PID control is the industry standard and is used to control many functions throughout the plant, including aeration. The acronym PID stands for Proportional Integral Derivative. This is the control logic or algorithm that is used to convert input data into output commands. The PID algorithm is shown here. Local system integrators, equipment suppliers, and consulting engineers all use this standard algorithm in their control solutions. For aeration control, there are three discrete control loops: a DO control loop that adjusts airflow to achieve a DO set point, an airflow control loop that adjusts a valve position to achieve an airflow set point, and a pressure control loop that adjusts blower output to achieve a pressure set point. Each loop has its own algorithm, and each algorithm is calibrated with specific P, I, and D constants to provide the desired level of operational control. The design for a pressure PID aeration control system is shown here. As illustrated, there is a DO control loop, an airflow control loop, and a pressure control loop. The loop structure shown is for a single zone. Since the primary machine being controlled in an aeration control system is the blower, blower manufacturers are the main supplier of aeration controls in the market today. This needs to change as controls become much more process specific. For systems with multiple control zones, this is how the system lays out. Keep in mind that each loop functions independently. In this example, we've shown 3 aeration zones. This translates to 7 control loops that operate independent of each other. Now that we have a cursory understanding of controls, let's go back and consider what level of control performance is required for satisfactory aeration performance. Clearly, low precision and low accuracy will not deliver optimum treatment performance. High precision and low accuracy is better, but this likely still falls short of assuring desired treatment performance. Low precision and high accuracy is acceptable depending on the level of performance desired from the plant. And of course, high precision and high accuracy is best, but this level of control may not be available or cost effective. Control charts are the telltale indicator showing the level of precision and accuracy provided by the control system. Time is typically recorded along the x-axis. If you are operating a municipal plant, be sure to review a full 24-hour period to determine how the control system handles diurnal variations. Industrial plants may require a different window depending on how the waste stream varies with time. The y-axis is a control parameter, in this case, residual DO. Every control zone has a control set point. The set point may not be obvious from the chart. Set points can also vary depending on the operating objectives for the plant. The yellow band represents a 0.5 milligram per liter operating control band. This represents the level of control being provided with best-in-class next-generation systems, including what EDI offers in its Symphony operating management system. When reviewing a control chart, consider the process application and how precision, accuracy, and stability impact the operating objectives for the plant. In this example, the control chart is for the main oxic zone in an MLE process at a mid-sized wastewater treatment plant. Overall, the operational control being provided at this plant appears to be poor, with low precision, low accuracy, and low stability. In this example, data is provided for 3 zones in an activated sludge process. The operating DO is shown by the blue lines, and the yellow band represents a 0.5 mg per liter control band. The level of control appears to be tighter at this facility. However, the level of control varies from zone to zone. As mentioned earlier, the PID control algorithm is applied in each control loop. This means that the P, I, and D constants need to be initialized and set for every loop, including the individual DO, airflow, and pressure loops. Typically, the control system is initialized at system startup. To better understand how the control system performs over time, let's review a 24-hour operating period. The data shown is from a large plant operating an MLE process. For the highlighted time period, the algorithm constants are tuned and provide excellent control precision and accuracy. A 0.5 mg per liter control band is shown for reference. As we know, the conditions at a municipal plant change throughout the day. For this time period, the constants no longer provide stable control. From a technical perspective, the level of precision is poor, the level of accuracy is good, and the level of stability is poor. Here, the operator has changed the DO set point. Again, the constants do not appear appropriate for the operating conditions. In this case, a high level of precision and stability are being provided, but the accuracy is poor. Over a 24-hour period, we see that the selected constants are well suited for specific operating conditions, but not all. From an application perspective, PID controls are not well suited for nonlinear processes with a lot of variation and lead lag. Unfortunately, we just described aeration control in high-rate activated sludge plants. At a minimum, PID aeration control systems require regular tuning to provide tight operational control. Tom Jenkins is a recognized expert in the aeration control field. This is an excellent reference to learn more about aeration control. As summarized by Tom, DO control is one of the most difficult control loops to implement since DO control is nonlinear, has significant process time lags, is a multivariable process, and has extreme variations in loading. These factors make the PID algorithm poorly suited for DO control. Up to this point, we haven't spent a lot of time discussing system stability. This is another limitation of PID-based aeration control systems. Let's go back and review the airflow data on this chart. Remember, each aeration control loop has an airflow loop. In this case, airflow is varied by adjusting the valve in the control loop. The amount of airflow variation present in zone 2 and 3 is significant. This instability directly impacts valve, actuator, and in some cases, blower service life. Biochem Technology is the provider of the controls being integrated into EDI's Symphony solution. The control loop structure used by Biochem is similar to PID, but different in several key areas. First, the control algorithms developed by Biochem are process-based and are specific to each application. This alternative logic allows the control system to function differently in response to set point deviations. In each case, a revised operating condition is calculated based on measured error and field operating conditions. Through repeat calculations, the control algorithm is calibrated in real time, so tuning is now completed continuously. While a PID system adjusts for errors, Biochem's next-gen controls account for errors. The efficiency provided with a control system that uses tactical operating commands is best illustrated by this flowchart. Step 1 in the control logic is to review the operating and target DO set points for the entire system. The output from this evaluation is a new airflow for each control zone. The system then calculates the total airflow demand for the system and provides a total airflow command to the blower master control panel. Then, the system determines the required valve positions to distribute airflow to each zone. This evaluation is completed using dynamic most open valve logic to ensure that losses in the system are minimized. Since these critical steps are completed simultaneously, the system receives a full bank of operational commands. The process is repeated, issuing a new set of commands, but only once every few minutes, which is a major distinction from PID-based systems. Instead of trying to constantly adjust for errors, this purposeful cycle frequency underscores the operational precision and accuracy of the system. The level of precision and accuracy provided with Biochem's next-generation controls is shown here. From a process perspective, DO is maintained within 0.5 milligrams per liter of the set point 95% of the time. Because the system is self-tuning, the level of control performance delivered does not change over time and is not impacted by short-term or long-term changes in loading. The operational stability provided is shown here. The top chart shows how airflow is modulated to maintain the aforementioned DO set point control. As expected, the airflow to the primary oxic zone is adjusted the most as the loading to the plant varies. Subsequent reactors require minimal airflow adjustment as load changes are mostly assimilated in the first zone. The lower chart shows how the valves are modulated using dynamic most open valve control. This, in combination with control of the blower flow, produces the airflow distribution in the top chart. The deliberate control action provided by the system is shown. In terms of control and blower equipment service life, premature failure of these components is essentially eliminated. Beyond the direct operational performance gains reviewed, the use of process-based control algorithms support a host of new deliverables that have not been historically available. Referring back to this example, let's again consider the question, what DO and why? Historically, DO set points were static, and while this provided the required process performance, static DO set points do not fully optimize the process nor energy use. From a design perspective, a constant DO operating strategy provides the critical level of treatment required at peak load. When the plant receives a load that is less than design, the treatment rate is maintained and full treatment is achieved well before the end of the tank. Under this operating strategy, endogenous respiration occurs, which lowers the net production of biomass from the system. Today, we know that nitrification varies as a function of residual DO. At 2 milligrams per liter, we are operating at near maximum nitrification conditions. At less than 2 milligrams per liter, the rate falls off significantly. This reinforces the merit of the historical rule of thumb for nitrification. However, the relationship provides an ability to match treatment rate to incoming load. With precise and accurate aeration control, we can now pace aeration so that the desired level of nitrification is provided at all times. By lowering the DO set point under non-peak loading conditions, the amount of aeration is reduced, and this saves money. We also changed the biology by reducing stress. This shows up in improved settleability rates and lower SVI values. Operating in this fashion also encourages denitrification, so we can enhance oxygen and alkalinity recovery, all while lowering effluent total nitrogen. The strategy I just described is the foundation for the biological process optimization control system offered by EDI. The operational logic of the system is shown in this chart. The system is a feed-forward system that adjusts DO set points based on influent ammonia and other environmental parameters. In this example, the DO is adjusted in real time in a swing zone and an IFAS zone. In terms of treatment performance, this shows the gains realized at a plant using dynamic DO versus constant DO. Let's shift the discussion and briefly review energy use and equipment performance and capacity. This particular plant has 14 aeration control zones. We have discussed what DO and why. However, we can also evaluate DO set points in terms of total airflow. Process-based controls optimize DO set points not only for process performance, but also lowest total aeration demand. Flow-based controls also reduce control system pressure losses. The discharge operating pressure at the blower can be reduced by as much as 0.5 to 1 psi. This saves 5 to 10% in power consumption. Capacity gains are also realized with systems using blowers with a variable output to pressure ratio. Another key deliverable is asset management. Process-based aeration control systems monitor aeration performance, so now we can start to quantify fouling rates in real time. This information is used to develop RCM prompts that are specific to the needs of the business. For plants seeking lowest total operating costs, maintenance is conducted when the restored performance saves more money than it costs. Similar protocols are available for instrumentation and mechanical equipment. With next-generation controls, every failure scenario has standard backup protocols. Thank you again for your interest. Now that you have a fuller grasp of controls and the impact of controls on the process, equipment, and costs of running the plant, we encourage you to learn more about the Symphony Operating Management System and how Symphony enables you to get the most from your plant.